Hello, good afternoon. So, our speaker of this seminar today, Professor Luis Rodriguez from Utah State University in Logan, a public university, well, state university. So, Luis, you can talk to him. His native language is Spanish. He was born in Ecuador, where he studied bachelor in mathematics, including 1 year stay at IMPA, very famous in the natives, Matemática
Instituto de Matemática Pura y Aplicada.
Then he went to Arizona State University in 2000. That's where we met. We were together in Tempe, in Phoenix. Then he got his PhD in 2004 in the field of classical analysis, so basic mathematics. Then he moved to applied mathematics, also at Arizona State University with Professor Carlos Castillo Chávez. I don't know if some of you know his name. He's quite famous in epidemiology. Yeah, quite famous book. Yeah. And in 2007, he was a professor in Puerto Rico, where he stayed for 4 years at the University of Puerto Rico in Mayagüez. Then later, also in mathematics and doing already applied mathematics. In 2000.
Sorry. In 2011, he spent 1 year in Ecuador, and since 2012, he's first tenure track assistant professor, and in the moment he's a tenured professor and a chair at the Department of Mathematics, University of Utah State University. And his current topics of research are mostly related to mathematical biology. There's several topics related to mathematical biology, and I think that you are a member of the group of mathematics of bio in the university. And today is giving us a talk in intermittent precipitation-dependent interactions encompassing Allee effect may yield vegetation patterns in a transitional parameter range. So
all right. Thank you very much, Manuel, for the introduction. And good afternoon, everybody. So I am very grateful that you're over here in this talk. Very grateful to the FISC for supporting this visit over here. I have had a blast of a time. I really enjoyed the city and the institute and the environment that I found over here. It's the first time that I am here in Mallorca. And I met Manuel when I was a grad student, and since then, well, we have been very good friends. And I had a chance, as Manuel mentioned, to meet Perry in a visit that he made in Puerto Rico several years ago. It was quite a good time. So first of all, I would like to know who over here is a graduate student. Can you raise your hands? Students, grad students, yeah. And undergraduate students? No, all right. Well, I'm looking at Zoom and see that perhaps there's a long list of persons over there. Maybe some of them are grad students too that decided to join us by Zoom. Okay, all right, okay, all right. So, well, yes, as Manuel mentioned, I studied mathematics, and then I saw the light and changed to applied mathematics, right? And particularly in problems at the interface with biology. But I'm interested in population dynamics and not so much at the cellular level, but to see the populations, at the level of populations. Some of my research has to do also with the pest invasions and control of pests. So I am not a PDE guy, and I am not a stochastics guy. I just like to see problems that are in nature and try to use the tools that are necessary to answer some of the questions that arise. And in this case, because I live in Utah, Utah is a very, very dry place, right? There are deserts, and the weather is very harsh. So the vegetation that developed over there is very strong, right? It's very resilient. And not only Utah, but also in the South, where I spent a lot of years too, in Arizona, as you may have seen from, if you have not been there, then for sure you saw Wild West movies, where the people is just walking and there's absolutely nothing but just this sagebrush going with the wind, right? So the title of this talk is a little bit long, and perhaps it doesn't say much, but I will go in a proper speed. So I hope that everybody, hopefully, and especially the grad students, will keep on the same page. So what happened is that, well, living in Utah, I saw all these variation of vegetation in the environment, right? And in one hand, on the other hand, you see, I saw a lot of research that has been done in the pattern formation in vegetation. There are books that have been written about that. Recently, a book by Meron, and there's also Ridolfi and Federico and other Italian authors that have done a lot of work in pattern formation and stochasticity and things like that. And I mean, those models are super complicated. I mean, very complex. They have advanced a lot. There's very smart people working on those problems. But at the same time, I, as a person that is trying to understand biology, right, I got interested in something that is called the Allee effect, right? So raise your hands if you know what the Allee effect is. Okay, all right. So if you don't, it's okay, don't worry. I will say some words about that because it's very important. So this Allee effect, which essentially is going to represent, oops, sorry, wrong button. Cooperation at low densities, competition. So these are interactions among vegetation biomass, right? And what I was interested originally was to see how can we extend this Allee effect in interactions in space, because you see, yes, there are plenty of models that deal with Allee effects, but they are what is called the physicists call the mean field model, right? But when you introduce space, there are new features that emerge that are important in modeling. And at the same time, to take a look at stochasticity in the model. But of course, when you say stochasticity, it could be many things. There are many different sources of stochasticity, internal to the system, external. And what I was interested is to take a look at stochasticity, only one source, environmental, and coming from events of precipitation, which can be snow or it could be rain and so on. So what happened is that the results that we obtained with my colleague, Cindy Greenwood at UBC, is that in some way combining these three elements gives us, or you can see the emerging clustering or aggregation of the vegetation. Now, it's different than patterns, right? I mean, when you take a look at all the models that have been written and studied very deeply, you see these fantastic patterns of stripes, or you see these hexagons, and you see all these symmetric things, and it's very nice. We don't obtain that kind of things. And in some way, it was, from the mathematics point of view, it was a little bit like disappointing because it's not that nice. But on the other hand, the results that we got are closer to what we see when we take snapshots in Google Maps. And take a look, for instance, this is a picture that I got in Google, a screenshot from the Sonoran Desert. Sonoran Desert is a desert in Arizona and Sonora, in the state of Sonora in Mexico, in which you can see these clumps of vegetation, and then you see the little dots, and then these things like tend to aggregate over here for some reason, right? And here you have another picture in which you have this creosote bush, right? That is typical in the Sonoran Desert. And this has to do with this Allee effect. Yes. What is the, the scale. Yes, thanks. So, okay. So you see this spot over here? Yeah, it is, the diameter of this is like around 5 meters. Yes, thanks. So, yeah, so this is one small of these. I know. So, no, there's more stuff there. There's more stuff, right? It's not just a single. So you see this picture, this is the bush, but you see there's other kind of vegetation in the bottom, right? And this is just an example of what is called an island of fertility, or fertility island, sometimes people call it. So, and I will explain this in a second. And this has to do, right? These clusters, right? In our model is going to be linked to the Allee effect. Now, the Allee effect, what is it? So there was a guy in the 30s, right? An American ecologist called Allee, right? The last name was Allee. And he was observing goldfish, right? And what happened is that he was interested to see what was the mechanism of the goldfish reproducing. So he had a tank of water, a fish tank, and then put goldfish over there and changed the alkalinity. And he observed that for different densities, the success of reproduction was different with the goldfish. But essentially what happens is that if you have enough goldfish that are in the fish tank, they release some substances, some chemicals that protect the eggs against excess of alkalinity, right? But while you have 2 or 3 little goldfish in the tank, and they release the eggs, they are not going to hatch, right? So it's the effect of combining the population that provide the protection to the fish. And he described that in papers in 1930s, and he didn't write anything about the mathematics. However, if you go to papers written in recently, they say, well, here we have the equation of Allee that he proposed in his work in 1930s, right? So yeah, so that's not true. Actually, it was Vito Volterra that wrote an equation for this kind of situation, but he was completely unaware of what Allee was doing. So it was very nice. One in Italy writing that, and the other in Chicago, seeing the same things, but experimentally. Okay, why do I come to this Allee effect? And well, unfortunately for those in Radioland, perhaps you're not going to see clearly what I'm going to write, but to understand what an Allee effect is, I will write just make one picture, this one. So I will say that X is the population of time t, population, okay? And this is the rate of growth per capita, okay? Okay, so for the students, perhaps you are of course familiar with exponential growth, right? So in an exponential growth in your high school classes, what do they say? You have dx dt. This is what? X. Yeah. So we can have a constant a rate of growth, right? So in other words, the per capita rate of growth is constant. Okay. So let's say over here. Okay. But in the Allee effect, what it means is that the per capita rate of growth is increases with the population. So instead of having a straight line, what you have is something like this. And that's all. So going back to the idea of the goldfish, I mean, the larger the density of goldfish in the fish tank, the better the options that the offspring will come out and survive. All right. Okay. Now, of course, what we have over here is you can assume that it's linear in the right-hand side, right? And of course, we can put x in the other side, right? You say, okay, we have that, but there's a problem with this equation, as you know from your elementary ODEs. The problem is that, Alex, what's the problem with this equation? Yeah, it blows up, right? So you need to saturate that with a carrying capacity over here, okay? And of course, things have to die, right? So you have a term that is a linear death over there, okay? So this is what we call the Voltaire equation. And of course, if you rearrange these terms, you can end up with something that looks like Rx, what is over here? K minus X, and then X minus L. Sometimes you can, well, you can factorize this thing. And this is what perhaps you have seen, this cubic described in the text as the Allee effect. And that cubic is used also in models for neuroscience. I think there is a Fitzhugh-Nagumo. And sometimes people say, okay, let's put this Allee effect and then let's add diffusion and see what happens. And well, there are many stories like that. But that's not the point right now. The point is just to understand what the Allee effect is, which is very simple. The rate of per capita growth grows with the density, okay? And essentially, that is what happened over here. So these fertility islands, you see, let me move the next slide, right? Every plant has a range of competition and a range of facilitation, right? So plants that are growing together, yes. The what? Oh, this is population density. Yes. No. We're talking about, in our case, about the vegetation, we look at biomass density. Yes, biomass. Mm-hmm. Yeah. So you see, you have this very rough environment. You have some plants that have been successful. Let's say a plant, well, this is schematic over here, or in the big bushes, they cover a little bit of the soil gets protected, the nutrients stay there. It rains, it doesn't wash off, the nutrients do not wash off. The insects are happy over there, they die there, they make the soil richer, and so on, right? And so it's a very rich region for growing over here. But what happened is that generally in the semi-arid landscapes, like the regions that I mentioned, the roots of the plants extend superficially to the sides and start sucking water and nutrients. So if there is a very unfortunate seed that falls over here, for instance, it will not survive because the environment is harsh and there are no nutrients, no water, kaput, all right? So when plants start to take this advantage of the facilitation, right? That's the word that you can use also, cooperation of low densities, then it is more likely that they will grow, right? But if they are far away, then it's very likely that they will, as seedlings, they are not going to be successful. Yeah. Now, what we want to do, I am going to show you is how we build this model, right? So we define this variable u, which is the density of vegetation biomass at location x and time t. Okay, and all right, and we are going to consider just a one-dimensional model, right? And we're going to look at vegetation that is j delta x away from x, right? So a certain distance, the vegetation that is at that point is going to exert an influence on the point vegetation at that location x. And it could be of two different kinds, right? Either it could be that it enhances or inhibits growth. Enhance growth because of cooperation, or inhibits growth because of competition. Now, what is going to be the contribution, right? So you see the vegetation at this new location, right, x minus j delta x, has some weight, right? And psi over here is a kernel. And this kernel we're going to choose as a Mexican hat kernel. So Mexican hat means that is the difference of two Gaussians. And if you plot a Mexican hat, it looks like, well, I have I have two Mexican hats plotted here. Right? The one that is in continuous line, so you see the curve comes from very close to zero, it goes down a little bit, and it goes up, and it goes down, and it's negative in this side. So it's like a Mexican hat. Everybody has seen a Mexican hat. In horizontal axis is the space, and vertical axis, well, it's just a measure of the influence. Okay. So in particular, these two ones over here we're going to use in a little bit in a way I'm going to tell you. Psi h is continuous line, and psi l is the dashed. All right. Okay. So of course, this Mexican kernel has nice properties. It is symmetric, right? And when when the space x is large, then the tail approaches to zero. Okay. All right. So what we are interested in is in the relative change of vegetation at exactly one point, right? At the point x during a short time interval delta t. So what we have is the change in biomass density divided by the biomass at location x and time t. So what is this going to be equal to? Okay. Yeah, that's a lot, but we're going to see piece by piece. Okay. So you see this in red. This expression has the cumulative effects, that's why you have the sum, of cooperation and competition. So you see these factors inside the sum is just what I wrote some seconds ago, right? And you see the sign of these terms could be either positive if it's cooperation, or negative if it is competition, depending of what is the sign of the kernel over here. Okay, and what we need is that certainly we need to regulate the growth. And what we're going to do, what we're going to do is to multiply by a factor, like it's done when you define the logistic, for instance. Okay, and of course things must die, so we have to add an extra constant. We assume a constant death rate of death. Then we let delta x and delta t go to zero. And we get this integral differential equation over here. Of course, you see, you have the dead as we had before, and we have u times this factor to control the growth. But of course, we have over here x squared, but well, this u comes from the other side because we were looking the relative rate of change. So it multiplies in the other side. So you see, if we drop the dependence on space over here, what happened is that we recover the classical Voltaire equation, right? So that's one thing that I liked, in the sense that it was an extension of the Allee effect that I haven't seen before, right? But what can we say about this model over here? Just to put that integral in the front, it complicates things a little bit. Now, what happened is that we can take a look at the homogeneous steady states of that equation. That's the first thing that you think about. And of course, what happened is that there are two possibilities: either zero, the state of extinction. Yes, please.
In the way you set up the spatial dependence, the kernel always both the quadratic term and the cubic term. So in the way it is in front of everything. So
Yeah.
The term of the real term and the saturation term.
Mm-hmm.
So how it has the same effect on both terms.
Yes.
I mean, other things one has in spatial dependence. I mean, typically one is that they are. I mean, in other, not in
Mm-hmm.
one, but in other fields, one might have the different term modeling different physical effects and have different sort of spatial dependence in the quadratic and in the
Yeah. Yeah. Well, in this case, we just
the way of
yeah.
one's goal was something.
Yes. So essentially, what we want is saturate the rate of growth. That's all what we wanted. Of course, when you see this minus x over k, you may think that as an additional dead, right? And you can think that, and it's valid. You may say, well, that may have a different rate of saturation. The extra dead that you have because of the competition close to saturation. But in this case, we assume that they don't. Yeah. Thank you. Okay. So there are two possible scenarios. First one, you have zero, the state of extinction. And then the other option is that you have three equilibria, either 0 and 2 non-trivial, one unstable and one stable. Okay? And you can compute those over here. You see, you have 0 and you start plus and minus. So the unstable has a special name in ecology. They call it the Allee threshold. Okay? So why is it called the Allee threshold? Let me just quickly make an important graph. Okay, so in the top we have the stable and the unstable. And this is called the Allee threshold. So depending on the initial conditions, I mean, if initial conditions are above the Allee threshold, then the population will thrive and everybody will be happy. But if you start under the Allee threshold, then the population is doomed. Okay? And this is what it's typically called the strong Allee effect. Now, what can we do with this information in our hands? All right. One thing that I have to mention here is the following. You will say, hey, the normal procedure is that you are going to take this homogeneous solution, the stable one, right? And then you will linearize around it. and then you will perturbate, right? And linearize around it and see if the perturbations can generate patterns. What is usually what people does, right? So for the parameters that we choose, right, for the kernels, it happens that the stable homogeneous solution, the homogeneous positive homogeneous solution is stable, all right? So after the analysis, you see, well, this thing you can perturb and it's still homogeneous. And of course, 0 is it's stable, right? And so there's absolutely no interesting result out of that. And I was going to say, I was thinking, no, this thing is not worth. I will not take a look at this anymore. But then I thought, well, we should put some, I would like to put some stochasticity in it. Yes. Yes, yes. But we wanted to put a kernel that we thought it's the parameters of the kernel are plausible, right? In biological terms. Yes. Yes, exactly. So we say, okay, this thing useless. But let's give it a little, one more shot. I thought we need to put some stochasticity. Now, you know, that's a pretty complicated business for people that is not stochastic like me, okay? But I tried to do something. So I thought, okay, what is the first source of stochasticity in the environments? Well, you have many things. I mean, you have temperature, you have the quality of the soil, you have wind, I mean, who knows? But in semi-arid landscapes, it's precipitation, right? And well, in a semi-arid landscape, in the desert, you have long periods with no rain, precipitation, or snow, and then just some a lot of water, right, in certain points in time, boom, 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 boom. And usually the events of rain by the eco-hydrologist is modeled as a Poisson process, right? That means that the time between events is going to be exponentially distributed. So I thought, hey, wait a second. So we have two kernels over here, and one of them can be associated to high precipitation, and that's why originally I put the H in the subscript that I didn't mention initially, right? In which you have lots of cooperation or facilitation at close ranges, and not so high competition at relatively far away, right? And the other kernel, the SARL, in which you have a very reduced cooperations because the vegetation biomass is competing for the resources that are there. You still have a little bit, but not much in comparison with the other. So one may represent the states of the system, one in the no rain, no precipitation, and the other some precipitation, okay, which is going to facilitate the growth. And now what I thought is, okay, we can combine these two things in the sense that we can stochastically alternate these kernels. So we are going to have actually two differential equations, which the structure is the same, but the kernel is different. And what is this thing going to do, right? Essentially, when we do this alternating stochastically, right, is that we go from one regime in the left, in which only 0 is the only possible state that is stable with extinction, of course. If there is not much rain, everything eventually will die, right? And the one in the right, in which this Allee threshold is switched on for some time, and that allowed the vegetation that is above the Allee threshold to grow up, right? Like in this case, okay? It grows. And whatever is under the Allee threshold disappears. Well, not disappears, it decreases, okay? So we're going to switch between between these two, but alternate stochastically because it's not a periodic thing. So we have these two combination of these two kind of dynamics. And then we see, let's see what we get when we do this. So you see this parameter P is the, okay, so I discretize that integral difference equation. And at every time step, I say, okay, with probability P, I'm going to choose high precipitation, and with probability 1 minus P, I'm going to choose the other one, the low precipitation. So running some simulations with P equals 0.12, you see horizontal axis is space and vertical axis is time. And we had chosen an initial condition that is just a Gaussian, right? And we observe in this particular simulation, remember, you're just observing a snapshot of a path, okay? The biomass density reduces to 0, it gets extinct. But if you increase the frequency, right, of the interchange of these two dynamics, at the beginning you see some transient, some rearrangement, it goes up, it goes down, and then suddenly, boom, something happens in the sides. You see these stripes that are created. And if you repeat this and obtain other snapshots, see another path, you observe this kind of results, okay? Of course, sometimes you obtain 0, but that's because it's stochastic, okay? So it's different every time you run it. And if you increase P, you increase the number of stripes, and you see the place with the locations, the range where the biomass vegetation is positive is enlarged. You increase a little bit more, and then you see just one big clump, okay? No stripes anymore. And the same thing for P equals 0.20 or 0.24. Yes, it expands, but that's because of the initial conditions, okay? I will explain in a little bit. So when I saw this at the beginning, I thought it was a numerical instability, right? So I said, what I'm looking over here, I don't understand what is going on. Why these things are being formed? How is the process that these stripes appear with the switching from one dynamics to the other? And what happened is the following. So I will give you the biological interpretation, okay? So here's one simulation at P equals 0.15, the frequency, okay? As in the other pictures, you see that there's some bunch of biomass that seems that it's going to be successful. It's going to perhaps make one big chunk of biomass, right? But no, that doesn't happen. So suddenly over here, if you take a look at T equal 150 over here, that's just a cut of that picture. But then you see at T equal 200, you start observing the formation of these stripes. So what is going on there? Okay, so this is a funny thing. You see that line over there, that red line in the bottom? Okay, that's the Allee threshold, right? So everything that is under the Allee threshold is doomed, cannot recover. Now, the vegetation density curve, it crosses the threshold, right? So what happens exactly at this crossing is that the vegetation that is above the threshold is going to grow, but it receives less competition of these poor guys over here because they are all dying and there's very low density, right? So they have the advantage of the asymmetry of competition. So they take advantage of that and they grow. But because they grow faster, more than the guys that are in the other side, these other poor guys have a less advantage. So they start going down, okay? And if the time that the system spends in the low precipitation kernel is long enough, then this competition is going to, you see this little arc is going to move downwards. And the thing is that if it crosses the Allee effect, the Allee threshold, sorry, then it's doomed. And that's exactly what happens here, you see? So it goes up, and then boom, goes down, and that's it. And that's the formation of this stripe. And then this effect just continues, okay? It continues doing so. Of course, there are many questions over here for which we don't have answers. For instance, what is the width of the stripes? It must be related to the kernels, but what is the relation? I have no idea. Yes, no, you have a question. Oh, it's periodic boundary conditions. Yeah. Oh, that's because of the initial conditions I chose. So I chose a Gaussian that is centered at 0. It's just because of that. Yes. Okay. So what I want to show you that this phenomenon is highly dependent on the initial conditions. So I run here 2 simulations with the same frequency, 0.12. The one in the right, I use initial conditions of a value 10 plus some arbitrary number that is uniformly distributed between 0 and 0.1. You see it's very small. And this one over here, in which is just uniform, equal to 10. And then I run the simulations on both sides. And in this one, you get the stripes, and the other you don't. And that's just because of the little variations, right? The little variations, and when the path is very close, is very low, right? And some of them cross the Allee threshold, then they are doomed, and that will improve the conditions of leaving out the others that are above the Allee threshold, and it will blossom. Okay, they will blossom. Then I have another picture over here, in which I have the same initial conditions for both pictures, right? But they are just 2 runs with the same initial conditions. But of course, because it's stochastic, then it has to give 2 different results. Okay. One is for p equals 0.10 and the other 0.08. So you see, sometimes the results that you may obtain are pretty sensitive to the parameter p. Okay. Now, one thing that I would like to remark at this point is the following. All right. So we have this dynamical system. We have this PD integral difference equation, and we have this kernel, one with high precipitation, one with low precipitation, and we are stochastically alternating between these 2. And it was very interesting that, you see, if you don't, if you put one of the one kernel, it is doomed. It will go to 0, the vegetation density. If you put the other one, then it will blossom and fill the whole space. All right. But what we're doing is that switching between these 2 and obtaining these clumps, this clustering, this aggregation in between. And that it's very, I mean, it was very nice to see that there actually seems to be parallel to the Parondo paradox, right? In which you have 2 losing strategies, but you can combine them in some way in which you get a winning strategy. And this was just fantastic. I mean, we were doing these things without knowing that, but later on we'd say, oh, look, there's already this kind of ideas that have been running around. And so the Parondo paradox. And later we found some papers by Katia Lindenberg. And perhaps some of you are familiar with her. I think she's in San Diego. I met her, but they have this idea of alternating. However, their results have to do with local alternation, right? While over here we have this alternation for the kernels in the whole space. So now, what else can we extract from this model? So you see, we take the Volterra equation, right? And because we have these kernels, we can compute the integral of the kernel and use it as the per capita rate of growth, as I showed initially in one of the slides. And then we can see what happened with what's the behavior of the mean field doing the alternation with these two different numbers, the integral of the kernel, right? So that's what happens over here. So for values of p, right, the parameter p, we're going to have that, p 0.14 dead, 0.16, we have some dead, and then some survival for the vegetation. And then, of course, if you have larger values, you'll get survival. And of course, if p is equal to 1, then you are only with pure survival, right? But we are interested to compare, okay, this is the mean field model. This thing that this animal does not include space, right? So can we compare these results with the model that, our model that includes the space? And that was my mistake. I put the 2 slides that are equal. Okay, so this is the one. So we compute the probability of survival of the mean field versus the spatial model. And this probability of survival is plotted against the value of the parameter p, right? The parameter for switching. So you see over here, these red asterisks are associated with the mean field model, and the blue circles is the results from the spatial model. So you see for, let's say, values of 0.14, the mean field mostly is going to tell you, hey, you are going to have extinction, but actually introduction in space helps to the survival, right? And not only that, but essentially is the switching with the Allee effect that helps. So I separate these the blue circles and put them here to the right, and just make a distinction when you have small clumps. And the small clumps are exactly in this region in which these two models have this discrepancy, all right? And of course, later on, after 0.16, both of them show survival. And in the case of the spatial model, there's this big clump. So as to finish this, what we can conclude is that, well, we have a model, a spatial model that integrates the Allee effects, competition, and the stochastic alternation of kernels that represent different regimes of precipitation, right? And this shows these patterns of aggregation, right, that seem to be independent. I mean, not independent, but different of the commonly known Turing mechanisms. One more thing is that we can actually appreciate how the introduction of space in a stochasticity give different results regarding the extinction, right? And also we see that the simulations and the results that we have seen are highly dependent on the initial conditions. And well, with that having said, I want to thank you very much for listening to me.
Some time for comments, questions?
Yes.
Well, I have many, but I'll do just
Sure.
one or two. My feeling is that in your initial model, so you say you discard parameters for which you have a Turing instability. So you have no pattern information for the parameters you use.
Yes.
But more likely your system changing a parameter will have a Turing instability.
Yes.
And will create a pattern.
Yes.
Okay, as a result of that kernel.
Yes.
So my question is, do you think that pattern that is created, no? If you assume you can change a parameter and you can create that pattern and then you change back your parameter where you are working, is that pattern surviving? I mean, there is pattern solutions for the parameters you are using for those kernels.
Oh, okay. Mm,
Feeling is that yes, that there is a pattern there as a nonlinear solution.
yeah,
So
yeah.
the
So
solution
let
has
me
a
see if I
stable-
understand. So you choose parameters, so you get an homogeneous solution, you perturb, you get a pattern. Now, you want to
Continue
get
the pattern back to the way you were, and that pattern may survive.
that pattern may survive. Yes. Yes.
So you have that solution as a nonlinear solution, okay? Not
Uh-huh.
bifurcating because you cannot access the bifurcation, but the nonlinear solution as a pattern exists. My feeling is that what you see is that pattern.
Oh, I see. I
Okay?
see what you mean.
And then next, the Lee effect, you have the Lee effect for the homogeneous solution, okay?
Uh-huh.
That's okay. But then that pattern has also an Lee effect, which is modulated. So you have
Oh, yeah, could you please repeat? You have
Yeah.
the Lee effect? Uh-huh.
so since that pattern is subcritical, okay, you have the high amplitude pattern, which is stable, the one you see, but there is a low amplitude pattern, which is unstable.
Uh-huh.
And that low amplitude pattern acts as an Allee effect, as an Allee threshold, which is modulated in space.
Mm-hmm.
And that threshold is typically lower than the homogeneous one. So that might explain why when you put this noisy initial conditions and you put the two kernels that jump,
Uh-huh. Uh-huh.
it's easier to cross that threshold than the homogeneous one. So that triggers the pattern.
Mm,
Just an idea. Huh?
it
That-
could be. I
Maybe it's
haven't thought about that.
maybe we could check this. There is
Yes. Yeah.
I don't know.
Thank you for the suggestions.
No more questions? No, that's not
Okay.
Well, I have a very simple question. You did the stochastic simulations. How many realizations did you consider for the different conditions for the two conditions that you put for the kernel?
How many simulations?
How many realization of the noise did you take?
Oh, well, the way in which it's built, you mean for these ones?
Yeah,
Okay, so what happened is that you're just observing one path. So in the discretization, so let's say you start with the low precipitation kernel, and then you ask in the next time step, will it rain or not with probability P? And then you choose the kernel to respect, you answer the question, and then you go to the next step and so on. Now for this picture, so I think that we got 10,000 for each one of these stars, and less for the circles. I think that we chose like 20 or 30, and we stopped there because, well, it was taking a long time. But yeah, the variance was very small. Yes.
I have a couple of questions. The first one is in the simulations that you show, the time that appears there is in the units of switching of the pattern, no?
Sorry.
So in these results, the scale of time is in number of times that you are switching the patterns, no? So when you have a time 200,
Yes, these are
yeah,
time steps.
each time step you switch the patterns.
No, it's just time. So it could be that in
So
three
what
steps
is
of
the
time.
time step of switching the patterns?
No,
No. With probability 12, you decide if the pattern switches or not. But what is the basic time in which you draw the dice? It's
oh,
the time
it's
step.
just one time step.
Yeah,
is
that's
equal to
my
one.
point. So
Yeah.
that time is in the units of times in which you decide if you will take one pattern or the other. No.
Yes, that's
Okay,
correct.
Okay,
That's correct.
Now, it seems that if you look at these two pictures here, that the wavelength of the pattern is independent of that rate. Is independent of the probability, because the first figure on the left and the figure or this one, not the one, this one and the second on the left, I mean, grosso modo, the wavelength of the pattern is more or less the same. And if you go to the next one where you excite a pattern that covers all that, the separation of the bands is very close.
Yes.
It's very similar to this one.
Yes. Yes.
So, which this means that the pattern or this dynamics that generates this pattern is not very much dependent on the probability to select the humidity pattern. It depends whether you see or not depends on the probability. But once you select the pattern that you observe is always the same or similar.
Well,
Which is on the direction of what Damian was saying at the beginning, that this is a piece of a pattern that our system might have for other parameter values. That of course, depending on the pumping, or also on the pumping, that's optics, but depending on the region where there is rain or there is region of the kernel, can be excited the whole system or just the central part, okay? But the pattern that you trigger is more or less the same. It is not fully regular, because as you see here, the wavelength is not exact, which is okay, because when you excite patterns which are disordered, sometimes you might be missing one of the wavelength. This is something that happens, for instance, in these whispering cavity modes in ring cavities of amplifiers, where you might be missing one of that. But the basic pattern behind seems to be sort of independent of everything. If you do a Fourier spectrum of this, the dominant wave numbers seems to be very similar to the ones that you get for the previous cases.
Yes, that's true. That's something that we don't, first of all, we have made just computations for a limited amount of time, 600 or so steps. So we don't know anything about the asymptotic.
If there is any instability there, it's going to take a huge time step. So if there is any rearrangement of the patterns that they are there, this is going to take forever. It might be, but it's going to take forever. I mean, in that scale could be, I don't know, forever. It could be, because there is interaction. Okay, you have a pattern. These patterns, they have a sort of tail. Okay, that when going to zero, and there is interaction through the tails. But this is very, very weak. So this will rearrange, but it will take forever. But if you look at just at what is now the dominant wavelength of this, of course, this is disordered, but the dominant, I think that the dominant wavelength here in the pattern there is more or less the same, which is sort of a pattern distorted, similar that we have observed in these whispering cavity modes.
So essentially what happens is that you see in time we know that, we suspect that there should be a limit stationary stochastic process in time. And the properties of that and how that may be related to Turing patterns, actually, we don't know. We have no results on that. Yes. So thank you for the comments.
More questions? One of the experts in vegetation patterns. I have one easy question. If you go back one or two slides. For instance, here. So as this is a stochastic problem, you said that sometimes you obtain, for this parameter value, sometimes on this, the condition is random, you obtain this result, and sometimes you don't obtain these results. How likely, how probable is that you obtain this regular result, and how likely is that you obtain something like this?
Like, you mean between extinction and...
Yeah.
Oh, not regular or extinction?
So for the same, repeating simulations for the same parameter, for the same P, how often do you get this, and how often do you get something else?
Okay, so depends on what the something else is. If the something else is extinction, then this histogram that I presented at the end answered that question. If it is regarding the stripes, the number of stripes, you see sometimes you see that there's a stripe in the center. You see that here you have one to the right, one to the left. Over here, there's one in the center. It depends on how quickly, you see, not all the stripes start appearing at the same time. And that is because of the regime that you had before, which is stochastic. So sometimes it may start upper, in which the number of stripes is going to be less, or sometimes it could appear earlier, in which it will be wider.
Sometimes it will start like here, so You wouldn't see at this fixed time.
Yes, correct.
Okay.
And sometimes you will obtain zero extension.
Okay.
Mhm.
Any more questions? Alex? Cristobal? Okay, then let's have the speaker again.
Thank you. Thank you very much. Oh, gracias.
Sí,